I'm John Hart, and I'll be teaching this course next semester. The course has 3 credits, and you can find out more information, including the syllabus and last year's lecture notes, on the website mechanosynthesis.com. And the course is a highly interdisciplinary course, drawing from knowledge in mechanical engineering, material science, electrical engineering, chemical engineering, and other fields, and it has 5 primary objectives. The first is to understand the fundamental properties of nanostructures, such as nanoparticles, nanotubes, and nanowires. In many regards, these can be considered building blocks for the new materials and devices that we want to learn how to make. And in my hands I have models of, this is a molecule of C60 made of exactly 60 carbon atoms, similar to the structure of a soccer ball, only this soccer ball is 1/50,000th the diameter of your hair, as well as here a carbon nanotube, also about 1 nanometer in diameter. And these materials, as we'll learn, have truly fantastic properties relating to the precise atomic structure, and their properties can change significantly based on the positions of their individual atoms. After we talk about the characteristics of structures like this, we'll talk about how nanostructures interact with one another and their surroundings, how they stick together due to intermolecular forces relating to how the individual atoms in one structure and the other interact, as well as with things like electric fields and fluid flows. Then we'll talk about how to make the nanostructures themselves by high temperature processes, by chemical methods, and then how to put them together so we can control their size and structure and placement. So going from one structure to the precise organizations of large numbers of structures, often billions or trillions or more, that are necessary to make macroscopic materials. And with that assembly, we want to understand how the properties scale based on how you put them together. For example, what's the difference between a property of an individual nanotube, which might be a perfect atomic structure, and a yarn of nanotubes that we would make by spinning billions or trillions of nanotubes together. And that's what we need to understand to make functional macroscopic materials that we can see and use for these new applications. And finally, the course will conclude by an effort to combine our knowledge to design new devices, materials, and processes, and we'll treat these with a set of case studies, also case studies throughout the course, and a course project where you have the opportunity to work with a small team and define a topic of your interest that can make a research proposal in one of these 3 areas. And the course outline much follows the objectives, starting out with a broad introduction, treating the properties of the structures, interactions, synthesis, assembly, and then the case studies and presentations. And the assignments consist of 5 comprehensive problem sets, 1 exam, and the project, which really is the capstone assignment of the course. Once again, you can see a syllabus and last year's lecture notes on the website, and feel free to contact me by email with any questions. And I think we really are at the ground floor of a lot of exciting technologies based on nanomaterials, and I look forward to an exciting semester. Thanks.